Disclaimer cause all materials in this video are for educational purpose only.
Training a network to become a great generator of images is kind of like training a student toward mastery of a subject. The student produces work, and the teacher needs to be very careful about how to set expectations of student performance. If teacher expectations are unrealistically high, the student can't meet them and won't learn. If teacher expectations are too low, the student has no incentive to improve and flounders unproductively. The teacher and the student will need to co-adapt. That is, while the student is learning, the teacher's expectations increase, and in response, the student's performance rises to meet the increased expectations. The generator and discriminator we talked about last time are in a similar situation. As the generator gets more and more adept at making realistic images, the discriminator should ratchet up its expectations, so the generator is being challenged to get better and better. We can design deep neural networks that carry out this kind of co-adaptation of a generator and discriminator using a design called a generative adversarial network, or a GAN. GANs are generative in that they include a generator component, like we talked about last time. They are adversarial because the discriminator is trained to challenge the generator. Putting this adversarial idea in the mix allows the creation of new images that are photorealistic. But GANs also open the door to what are sometimes called deep fakes. The number and variety of GANs exploded starting in 2014, with as many as 500 types introduced in less than 5 years. A website was created called The GAN Zoo, just to document all the different species of GANs that appeared. Some of the names are pretty punny. Gandhi, vegan, elegant. One paper specifically described how to train your drag GAN. GANs have been used to solve a variety of image problems, especially in the context of generating photographic quality pictures of non-existent people, places, and things. GANs can also make a person look older or younger. Here's me and an aged version of me. I look a lot like my dad. Here's me and a regressed version of me. I look more like I think I look, and a bit like my son. GANs can automatically conjure up a revised landscape after a building is removed. Tools like Photoshop have long made it possible to modify photos manually, but GANs can make these modifications completely automatically. In general, the simplest applications of GANs go like this. Given a collection of images from some class, generate a new image that belongs to the same class. If the class is photographs of faces, it generates a new face. If the class is floor plans of bedrooms, it generates a new bedroom floor plan. If the class is cartoon characters, it creates new cartoon characters. Generating new characters could be beneficial in movie production. For example, scenes in the movie Lord of the Rings include battles with tens of thousands of separate characters. With the advent of GANs, movies could be more easily populated with detailed, realistic individuals, each different from all the others. In the previous lesson, we tried to solve the problem of drawing a daisy. Our high-level strategy was to consider the creative process as consisting of two modules, a generator and a discriminator. The generator produces images, and the discriminator judges them. To construct a discriminator, we started with a convolutional neural network that was already trained to a high degree of accuracy to recognize daisies and camels and screwdrivers and hundreds of other categories. We then modified the image automatically using gradients to move it in the direction the network believed would be most daisy-like. The result was not daisy-like at all, at least not to humans. So what went wrong? To a first approximation, we were not asking the network to create something more daisy-like in any absolute sense. We were merely asking the network to use low-level differences in the pixels to create something that was more daisy-like relative only to the other kinds of images the network happened to be trained on. To say it another way, the VGG16 discriminator is only good at distinguishing daisy photographs from other typical photographs, but it has no idea what a daisy really is, so it can't tell the difference between a daisy photograph and a random field of pixels that includes some low-level features found in daisy images. Simply put, it wasn't trained to do the higher-level discriminating we need. Clearly, we need a better discriminator. But we don't know a priori how to tell the machine what the discriminator needs to be good at discriminating. The GAN insight is that we can pit the discriminator and the generator against one another. We already know that the generator needs to be good at producing images the discriminator accepts, so we can use the output of the discriminator as a loss function for the generator. The more the generator produces images that the discriminator likes, the better. The discriminator, meanwhile, is no longer going to sit around to be taken advantage of. Instead of a static discriminator that the generator can outwit using only minor low-level changes to the image, we will train the discriminator dynamically to do a good job of distinguishing real daisy photos from the actual output of the generator. Our co-adaptation goes back and forth many times, retraining the generator each time against the current discriminator, and then retraining the discriminator against the current generator. The hope is that this back and forth process creates the right kind of moving target that will lead to steady progress. To get the basic idea, let's work through how we can generate a very simple kind of artificial image. These three images each consist of 20 random grayscale values constrained so they increase in brightness from total black on the far left to complete white on the far right. For ease of reference, I'll call this kind of image a staircase because it's a sequence of steps from dark to light. Each staircase goes from 0 for black to 1 for white, but each staircase is slightly different from the others in that the specific shade for each intermediate step can differ between the staircases. Here's a snippet of code that generates m staircases of size d. To start, a bunch of 0, 1 uniform random numbers are arranged in an m by d matrix. The code then computes a running sum, also known as a cumulative sum or cum-sum, across the rows of the matrix. NumPy refers to moving across the rows as traversing axis 1 of the matrix, so that's the parameter value we will use in the call. So now we no longer have a bunch of random numbers between 0 and 1. Instead, each row contains the running sum at each location. This procedure guarantees an increasing sequence with a starting value that is somewhere between 0 and 1 and an ending value around 10.0. It's not a staircase yet, since a staircase goes from 0 to 1. We can rescale the values so that they're in the right range. First, we grab the minimums, or mins, of each row in a vector x. Since the rows are increasing, the min must be on the far left. We subtract off these mins. We then grab the maximums, the maxes, for each row. They are on the far right. We divide the vector x by the max values so everything is in the 0, 1 range as desired. Then we'll get a network to learn to produce these one-dimensional grayscale staircases. Staircases are a nice stand-in for the more complex two-dimensional color images that GANs typically produce. Once we've mastered them, we can graduate to photographic images. Here our goal is to train a network to produce novel staircases using the artificially generated staircases as examples. In the previous lesson, we tried using a recognizer as a discriminator and then iteratively improved a random image via gradient descent to generate an image that the recognizer believed was in the target class. That approach did not work for daisies, but staircases are much simpler. Maybe we'll have better luck with the gradient descent approach here. The simplest way to train a classifier to be a discriminator is to just use two classes. One class should be staircases, of course. The other class should be non-staircases? But what does that mean? To train the classifier, we need specific bad images to act as a foil against which the staircases can be judged. Let's take our alternative class to be scrambled staircases. That is, we'll generate a staircase, then swap the steps around so they aren't in sorted order. This process provides an informative contrast for staircases because individual steps are all of the type that could appear in a staircase picture, only the order is off. We can generate random non-staircases by starting with a set of positive examples, xpos, which are produced by running the function makeposMD. For this matrix, we can apply a random permutation to each row using NumPy's applyAlongAxis function. The resulting collection of negative examples is assigned to the variable xneg. Here's a row of the resulting matrix, a set of scrambled gray bars. For our classifier, we'll create a simple neural network using Keras. Our network has d equals 20 input units to correspond to the 20 steps. There are 10 hidden units that the network can use to compute, and there are 2 output units corresponding to staircase or not staircase. The predictions in the output layer use softmax activation. Softmax accentuates the largest value in a vector, then normalizes the values to look like probabilities. That is, the values from softmax are between 0 and 1 and sum up to 1. We can train the network with 10,000 randomly generated images, half staircase and half not. We train for 15 epochs. The resulting network has 100% accuracy in distinguishing staircases from non-staircases, which seems great. Now that we can accurately discriminate between staircase images and scrambled staircase images, let's use the gradient approach to turn a non-staircase into a staircase. We'll take steps in the direction of the computed gradient until the image is recognized with over 95% confidence as a staircase. We'll want the staircase, which is represented by a vector input data, to remain a valid image. To keep the values of the vector in the right range, we reset back to 0 any values in input data that have gone negative. Now, let's use our learned staircase discriminator to try to help generate a staircase using gradients. We start off with a random non-staircase, shown here at the top. The bottom image is the result. The highly accurate classifier recognizes that the top image is not a staircase, but it thinks the new output is a staircase, even though it is not. Check out the very dark bar near the middle, or the white bar 3 steps to its right. Those bars are out of place. Let's look more closely at how the top image gets modified to become the bottom. On the left side, the steps are darkened all the way to full black. And on the right side, the steps are brightened towards entirely white. It does seem as though the discriminator is paying attention to whether an image has darker steps on the left and brighter steps on the right, but it doesn't understand that all the steps need to be monotonic as we go from left to right, consistently changing in the same direction at every step. Whatever rule of thumb the discriminator learned was pretty effective with the original dataset, yet it does not capture the real staircase concept we had in mind. So let's try the GAN idea. It's adversarial, so we need to construct 2 networks. The discriminator network is like what we had before. It takes as input a vector of size d equals 20, representing the purported staircase. It has 2 fully connected or dense set of weights leading to hidden layers, each of size d over 2, or 10. Finally, the output layer is a single unit that should output 1 for a real staircase and 0 for a fake one. Since we know this output value is between 0 and 1, we can use a sigmoid activation function. Sigmoids smoothly transition from near 0 values for negative inputs to near 1 values for positive inputs, which guarantees the output stay in a 0 to 1 range. The second network, the generator, is new, but it has a similar structure to the discriminator. In the non-adversarial generation process, we just used the discriminator's preferences to search for something the discriminator liked. This network structure generator maps a vector of noise into a staircase vector. The number of components of the noise vector can be thought of as a latent dimensionality of the image space. The more noise components, the higher the latent dimensionality. We'll use latent dim to be a variable that specifies the number of random values we'll use as our input. You only need 18 random values to make a staircase of 20 steps, since the first value of the staircase must be set to 0 and the last value must be 1. I picked 50 for latent dim, so the network would have a large pool of random values to choose from. The generator uses a dense layer of weights to map the chosen 18 random values to a hidden layer where the number of hidden units is 2 times d, or 40. The generator then has another dense layer of size d equals 20, then an output layer of size d equals 20. Since all the outputs should be between 0 and 1, I set the activation function for the output layer to be a sigmoid of each of these units. The generator and the discriminator are separate networks, but they are part of a grander whole. They link together through the generation of a staircase. The generator produces the staircase, and then the discriminator judges whether the staircase is real or not. The discriminator can get its input from the generator, which should classify as fake, or from the training data, which it should classify as valid. We'll use the Atom Optimizer for training, and we'll train for 30,000 epochs. The Atom Optimizer is an adaptive algorithm introduced in 2015 that controls the process of gradient descent by optimizing the rate of learning at each step of the optimization process. Atom generally does a good job, and it quickly became a default choice for training networks. We'll give the network a batch size of 128 examples in each epoch. We'll set up our training set X using only positive examples of staircases. We also create targets for learning. We use 1s for valid examples of staircases from the training set X, and 0 for fake examples that come out of the generator. Next, we construct the combined network. We build the discriminator and set it up to be trained. We can then instantiate a generator and call it Z, which will take noise inputs and produce images, IMG. We want to train the generator to make staircases that the discriminator cannot reliably distinguish from the real staircase images. In short, we want to fool the discriminator. The weights of the discriminator need to remain constant while we update the generator. If we did not hold the discriminator's weights fixed, gradient descent would solve the problem of fooling the discriminator merely by making the discriminator less accurate. So we set discriminator.trainable for the combined network to be false. The discriminator assesses the generator's image output IMG, and produces a judgment as to whether the image is valid. The combined network, end-to-end, connects the input Z to the output called valid. Now that the network is set up, here's how we train it. We've already seen two different strategies for training using Keras. The high-level strategy is to set up a network and some data, and then call fit to do all the work of training. We trained a classifier for staircases via this high-level fit method. The low-level strategy is to define our objective directly in terms of operations on arrays of data, referred to as tensors, that Keras can manipulate. Then we can have Keras take gradients of the objective with respect to the parameters, and we can apply those gradients to update the parameters. We applied the low-level gradient method to search for images of staircases that satisfied the learn classifier. But for GANs, we need a third, mid-level strategy that lets us interleave updates to different weights. To understand this mid-level strategy, it's important to understand the notion of a batch. To make deep networks train efficiently on modern hardware, we need to break up the training data into smaller units called batches. These batch units fit into memory and can therefore be processed much faster. The high-level fit approach in Keras handles breaking the training data into batches, computing gradients, and making updates to model parameters all on its own. But a GAN involves two networks, so to train a GAN, we need to use each batch in two different ways. We need to use it to adjust the weights of the generator, so it can make inputs that fool the discriminator, but we also need to train the discriminator to distinguish even the improved output of the generator from the real training data. Using batches in these two ways means we need more detailed control over what happens during the processing of a given batch. We'll update our weights with respect to each batch of data using a Keras function that updates the weights of a network based on a single batch of data. Using this train-on-batch function will allow us to implement our mid-level strategy. In each epoch, we create a batch of training examples. We make each batch of images from the training data by picking the indices of a set of training examples, X's, at random, and then pulling out the corresponding instances as IMGs. We also create an input set of random noise and feed it to the generator to get some artificial images we call gen IMGs. We train the discriminator to classify the real images as valid and the generated images as fake. Train-on-batch returns the loss resulting from the batch training. Now that we updated the discriminator, we update the generator. The generator is part of the combined network. Given the noise input, we want to update the generator's weights to make the discriminator more likely to classify the fake images as valid. So Given noise input, we want to update the discriminator part of the combined network so that the output label is fake, but we simultaneously want to update the generator part of the combined network so the output label is the exact opposite, valid. If we run the code on positive examples of staircases, the GAN learns to produce staircases. After 20 iterations, the generated images are already showing a propensity for darker bars on the left and lighter on the right. But they're not yet internally consistent. After 90 iterations, the staircase structure is starting to emerge. You can see black bars consistently on the left and white bars consistently on the right. In between, things sometimes get a little muddled. After 190 iterations, the staircase structure is much more consistently generated. The generator has learned to produce very good staircase facsimiles. One way to measure how close the generated staircases are to being perfectly valid is the number of pairs of steps that are out of order. Since there are 20 steps, there are 20 times 19 divided by 2 equals 190 possible pairs of steps. In a valid staircase, 0 of these pairs are out of order. In a randomly permuted staircase, on average, half the pairs are out of order. That's 190 divided by 2, or 95 pairs. Running the gradient approach improves things somewhat, resulting in an average of 48.4 pairs out of order. After 90 training steps, the GAN generator has improved things to an average of 18.6 steps out of order. After 190 steps, a few hours of running time, the GAN generator produces staircases with an average of only 8.4 pairs out of order. Even 8 pairs of steps is far from a perfect staircase. But keep in mind that we didn't have to give any explicit training to the learner about minimizing this quantity. It's just trying to make staircases that the discriminator cannot reliably distinguish from the real staircase images. We could have given it more processing time, but it already does a pretty good job. With this technology in hand, can we generate some daisies? If we want to make daisies, we need images to train on. I made a dataset of 124 daisy close-ups by searching online for daisy pictures that are freely shareable and then clipping out just the flower part using standard image editing tools. I scaled all of the pictures down to 36 by 36 pixels because that's the smallest picture I had clipped out. As we saw in lesson 14 on vision, densely connected networks, like we used in the staircase example, are not what we use for recognizing images. That's because dense networks don't have position invariance built in, forcing the network to have to learn to recognize items independently in each part of the image. So a better choice would be convolutional layers, which do have position invariance built in. But this generator needs to act like an inverse convolutional network. That is, whereas a convolutional network allows for groups of neurons that map a patch of an image to a class, we need layers in the generator that produce patches. In Keras, the inverse layer to the two-dimensional convolutional layer, conv2D, is upsampling 2D. Our generator for the DAISY case will make use of these upsampling layers. Take a look at our example code for the details. With revisions to the discriminator and generator both in place, we can run our GAN approach on the DAISY images. You can get an idea of what the generator does by feeding it different patterns of random noise and seeing what comes out. After one iteration of training, the generator produces fuzzy splotches of green and blue and black. After 40 iterations of training, the generator has added yellow to the mix, and we're starting to see the bright colors clumping in the middle of the frame. After hundreds of iterations of training, the network sorted out that there should be a yellow patch in the middle, white around it, and occasional flecks of green here and there. Looking at the image, we can imagine that something DAISY related is happening. But it could also just be a bunch of fried eggs. It's still hard to tell. After thousands of iterations, the images have become less impressionistic and more photographic. The pictures are pretty clearly daisies now. The petals are in focus, and the generator is pretty consistent. Not too bad, especially for low-resolution 36 by 36 pixel images. With higher quality DAISY pictures and even more training time, this approach would produce imagery that would be very difficult to distinguish from nature photographs. Ian Goodfellow pioneered the use of GANs in 2014 during his PhD at the University of Montreal with deep learning pioneer Yoshua Bengio. The photo shown here is not Ian Goodfellow. It was generated by a GAN accessible through the website This Person Does Not Exist. Each time you visit the page, it creates a never-before-seen human face for you. The quality of the images is amazing. Note how the colors of his eyes match, and the stubble on his chin matches his eyebrows and hair. It's quite hard to tell that you're not looking at a real person. As image generation technology improves, however, it may become impossible to spot glitches without sophisticated analysis tools. In all likelihood, it is the GAN technology itself that will provide the tools for catching fakes. As they say, the only thing that stops a bad guy with a GAN is a good guy with a GAN. In the examples we've seen so far, including the fake face, the generator networks are given noise patterns as input, and then transform the noise into images. The use of noise is what allows the same network to produce a wide variety of outputs. But there's no reason we can't also train a GAN to use other images as input. For example, we could train the generator to use random photos of apples as their input and then generate photos that look like oranges. If we have a data set of apples and a data set of oranges, we could use the apples to generate oranges and the oranges to generate apples, training both generators and both discriminators simultaneously. Wouldn't it be neat if the generators learned to transform the apples to oranges and vice versa so that they kind of look like each other? If we train the two GANs in parallel, there's no reason to expect any kind of relationship to develop between the two types of images. But there's a clever technique that links the two GANs so they end up mapping between the two types of images. The technique is called a cycle GAN, and it adds another component to the loss function used during learning. Specifically, a cycle GAN trains two GANs, one for generating images of type A and one for generating images of type B. Each GAN has a discriminator and a generator like before, but the loss function for each of these generators includes another element. It requires that plugging together two generators results in reconstructing the input image. That is, suppose we feed a picture of type A into the type B generator, and then take the resulting image from B and feed it to the type A generator, we should get the same picture of type A that we started with. To say it in mathematical language, the two generators should be inverse operations. So if the orange generator takes apple 1 and uses it to make orange 2, the apple generator should turn orange 2 back into apple 1. To make the network have this inverse property, we need to include a component in the loss function that compares the input apple to the two-stage output apple. That loss can be the pixel-wise comparison we used in lesson 18 on style transfer. An amazing observation is that adding this cycle GAN constraint when training the two GANs encourages the generator outputs to be as close to their inputs as possible. When the two GANs are locked in this tight dance together, each is focused on the other. Thus, the orange generator doesn't just produce an orange, it produces an orange that corresponds visually to the apple it was given. The 2017 paper that introduced cycle GANs provides 3 different usage examples, each of which can be run in either of the two directions. Cycle GANs can be used for artistic style transfer, like turning a photograph into a Monet-style painting. Thus, cycle GANs provide another approach to the style transfer problem we saw in the previous lesson. Cycle GANs can go beyond style transfer to do object transfiguration, like turning a horse photograph into a zebra photograph. One thing I really like about the horse-zebra example is that the generator leaves the horse mostly intact and adds stripes, but it also dries out the grass and darkens the sky to better match the African landscapes where zebras are found. Cycle GANs can carry out rendering transfer, like taking a satellite image of a part of a city and turning it into a map view. These maps are also a sort of two-way street. That is, the learned networks also know how to turn a map into a corresponding satellite image, adding whatever color and detail is needed. So it's not just changing a landscape, as in the horse-zebra transfiguration, but it's adding aerial landscape features to a map that didn't have any at all. When we use machine learning to make images in the generator-discriminator framework, designing good discriminators is very hard. As we saw with daisies and staircases, a discriminator can seem to be very accurate on a fixed data set, while badly misclassifying examples produced by a generator. What makes all kinds of GANs so powerful and so revolutionary is that they dynamically construct their own discriminators as part of the training process. By creating a discriminator that is explicitly tuned to the current capabilities of the generator, the discriminator is able to slowly ramp up, forcing the generator to be better and better at reproducing the kind of detail of real images. GANs need a lot of image data to be trained, but they do not need labels on those images. GANs represent a powerful and flexible methodology, creating state-of-the-art images of everything from apples to zebras. And GANs can also be used to generate other kinds of low-level data, like sounds. In the next lesson, we'll look at networks that can extract language information from sound, the problem of speech recognition. A milestone in the ability of machines to recognize human speech was reached in 2016. That's when researchers at Microsoft announced that their speech recognition system was achieving accuracy rates beyond human transcriptionists. Basic voice interfaces driven by machine learning have been broadly deployed since around 2011, and they've been improving ever since. Companies like Microsoft, Amazon, Apple, Google, and Baidu have all made important contributions to developing and disseminating speech recognition technology. Given how common speech recognizers have become, it's worth noting the limitations on earlier systems to understand how things have changed. There are three principal dimensions in which speech recognition systems have been limited. Some systems could only handle disconnected speech, with gaps between each individual word. Others were built only to recognize words from a limited vocabulary, like the digits 0 through 9, or names of cities on a train line. Still others are speaker-dependent and have to be tuned to work with individual users. Older systems improved to the point where they could overcome any two of these limitations, but it was machine learning systems introduced since 2011 that have been able to address all three challenges at once. The history of speech recognition approaches shows us how this complex problem was decomposed into simpler problems that could be tackled separately. Later, deep neural networks were applied to each of the separate problems, resulting in rapid progress. Since we'll be turning speech sounds into text words, it's worth getting a clear idea about what sound is. Sound is just difference in air pressure traveling through space. To visualize the movements of a sound wave, imagine we have a tube filled with air molecules. We'll pull back a plunger, causing a low-pressure region to form. When we push the plunger forward, air molecules are thrust forward along with it. They bunch up, then bounce off each other, causing other molecules to lurch forward and bunch up. The bunch travels along the tube of air at the rate at which molecules move and interact. The rate of travel depends on overall air density, and air density depends on pressure and temperature. That is, the wave moves more slowly in the cold, thin air of Mount Everest. The rate this wave propagates is known by another name, the speed of sound. It's about 750 miles per hour, almost 350 meters per second. In day-to-day life, the role of the plunger in this example can be played by the movements of all sorts of objects in the world. The movement and resulting sound can be organized or disorganized. Disorganized movement is like the crumpling of paper and results in a disorganized pattern of sound waves. Organized movement is like the beating wings of a fly. Organized movement causes the waves to arrive in a very regular, very organized pattern. A typical housefly, for example, flaps its wings 190 times per second. Our ears register this consistent pattern as a tone. We can depict the pressure measured at our ear as a function of time. Very roughly, the human ear can detect sounds up to about 20,000 times a second. That implies the ear is sampling the sound intensity function at roughly twice that rate. We'll call that the sampling rate. It's about one sample every 24 microseconds. Two values are enough to summarize a nice clean pattern like a consistent tone. The first is the height of the waves, that is, the pressure difference between the highest and lowest pressure parts of the wave. That's what we usually refer to as volume, or loudness, or intensity. It's also known as the amplitude. The second is the time elapsed between the peaks. The number of peaks encountered per second is called the frequency, and that's what we hear as pitch. Higher pitch, beep, sounds have frequencies like 255 peaks per second. Lower pitch, boop, sounds have frequencies like 85 peaks per second. More complex sounds, like the human voice, have more going on than just a single tone with regular peaks. It can contain multiple frequencies at the same time. A really helpful way to characterize speech is to plot which frequencies are present at each moment in time. This display is called a spectrogram. Here's a spectrogram of me saying no. No. The x-axis is time, and the y-axis is frequency. The third dimension is brightness. A bright white patch in the image means that there is high amplitude. Notice it can be bright for several frequencies at a time. The time axis underneath is labeled with the sound I was making at each point. You can see where the sound starts with a bright patch near the bottom of the image. The transitions to an and bright patches appear above it in the spectrogram. The O part is visible as a drop in pitch from the line marked 2000 down to about 1000. When the word ends, you see a return to the background pattern. The white bars in this image are called formants because they are the tones that we shape with our mouths to form speech sounds. I'm told that some people can read spectrograms, reconstructing what was being said just by looking at the pictures. I haven't been able to pick up that skill yet. But that is essentially what a speech recognition system needs to do. It needs to turn this kind of data about the speech sounds into text words. Now you understand the problem. How do we solve it? The earliest work on speech recognition dates back to a digit recognition system built by Bell Labs researchers in 1952. Computers were too slow back then to process speech information. Remember, auditory information comes at a rate of about 40,000 times per second, or once every 25 microseconds. The year 1952 was a decade before computers could even multiply numbers at that speed, let alone carry out a complex speech recognition algorithm. As a result, the researchers built their specialized recognizer directly out of electronic components like vacuum tubes. The system extracted the strongest and the second strongest formants, the frequencies with the highest intensities. Then they compared the formants to a set of 10 templates, one for each digit. The templates were kind of like specialized classifiers, but they were not built using machine learning algorithms. The templates were painstakingly created and tuned by people using trial and error. It was data-intensive work for people to do by hand. The system they built was reported to have an accuracy of over 90%, at least for one of the researchers who built it. For other people, accuracy was quite a bit lower. The Bell Labs system suffered from all three of the limitations I mentioned for traditional speech recognition systems. It was tuned for a specific person, it required gaps between words, and it could only handle the names of the 10 digits. It was a remarkable achievement, but not really ready for prime time. Things improved gradually in the 1960s. Researchers attacked the problem of phonetic segmentation. That is, approaches were introduced to try to break connected speech into smaller units, words, so the individual words could be recognized. Template patterns for words were introduced and could be matched against incoming speech sounds. Researchers realized how important top-down influences and context were in disambiguating sounds into the desired words. Did Bob Dylan say, "The ants are my friends," or "the ants are my friends"? Phonetic segmentation helped with connected speech and, to some degree, recognizing larger vocabularies. But since things were still primarily being done by hand, scaling up to more speakers and larger sets of words would have required prohibitively expensive amounts of expert human effort. The 1970s brought faster machines and a new machine learning technology that greatly improved the scalability of speech recognition systems. The technology is known as hidden Markov models, or HMMs. Hidden Markov models belong to the Bayesian style of thinking about machine learning. The fundamental idea is to view the relationship between input and output backwards. We build a model that goes backwards from text words W to speech sounds X. The models are hidden in the sense that they include latent or hidden variables. An ordinary non-hidden Markov model is called a Markov chain, after Russian mathematician Andrei Markov. Hidden Markov models were the best game in town before the first deep learning models began to be tried in speech recognition around 2012 or so. After that point, hidden Markov models were no longer central to speech recognition, although they have remained a mainstay in specialized machine learning solutions in signal processing. The Bayesian view says we should think about the speech signal as being generated by the text-word sequence, even though we don't observe the text-word sequence. And that generative process can involve intermediate steps along the way. Those individual steps might be the words that make up the sequence, or they might be basic speech sounds, called phonemes, which make up the words. Okay, so when a Bayesian system receives an input of speech sounds, X, it needs to reason backwards to possible text word sequences to find the text word sequence W that is maximally likely. We want to maximize the probability of the text words given the speech sounds, written probability of W bar X. We want to know what was probably said given what I heard. Argmax is a math operator that reveals the text words W that make the given argument or expression take on the biggest value. As we saw in lesson 6 on naive Bayes, Bayes' rule lets us translate between the probability of W given X and the probability of X given W. The rule tells us to rewrite the probability of W given X as the probability of X given W times the probability of W divided by the probability of X. We can view the probability of X in the denominator as just a normalization factor that doesn't affect which W is more probable. That leaves us with just two quantities. The probability of X given W tells us how words are pronounced. You give me a word W, I'll produce the speech sounds. It's the pronunciation model. The probability of W expresses which sequences of words are more likely than others. It's known as the language model. We saw this quantity in lesson 17 on text generation. A language model is what tells us that the sequence no wide pre 4 to 8 is less common than no I'd prefer to 8. Hidden Markov models capture the probabilities of sequences. They're especially useful for the part of the Bayesian model where phonemes are mapped into frames, slices of the spectrogram. Take a look at a set of slices that makes up an example of me saying the O sound. For American English, O is not one constant thing, it morphs over time. Think about your jaw as you say the sound O. It closes a bit after you start making the sound. That change in mouth shape creates the change in the sound. O. The precise duration of a part of the sound and the speed at which it changes will vary from one utterance to another. To simplify, let's express the slices of the spectrogram in a more cartoon form. Now we can imagine that there's a relatively small set of slices and that the overall sound is built by lining them up in order. The sound becomes 4 different spectrogram slices. Slice 1 appears twice in the sequence. Slice 2 appears twice in the sequence. Slice 3 appears once in the sequence, and then slice 4 appears 4 times in the sequence. The exact number of repetitions of each slice and the exact shape of the spectrogram for that slice will vary from utterance to utterance. To capture this variability, we change these 4 slice types into a kind of probabilistic machine. Consulting its specific probabilities, it spits out a spectrogram slice and then randomly stays in the same state or progresses to the next state. A hidden Markov model is precisely this kind of machine. It has a set of hidden states that generate observable outputs. Internally, these states transition from one to another with some degree of randomness. It's a randomized sequence generator. The parameters that control the behavior of the model are, first, the probability of transition between each pair of states, and second, the output probabilities, which determine what slice type each state produces. How can we learn good settings for these parameters? Well, if we had lots of data of O sounds where each slice was tagged with the hidden Markov state that produced it, well, then the learning problem is really easy. To estimate the probability that state 2 transitions to state 3, for example, we just count up the number of times the machine was in state 2 and then look to see how often it was next in state 3. In this example, 3 out of 5, or 60% of the transitions from state 2 go to state 3. To estimate what spectrogram is produced by state 4, we can just average together all the spectrograms associated with state 4 in the data. All of that's great, but speech sounds don't come with hidden Markov state labels on them. It's impractical to ask people to produce these labels, labeling each 10 millisecond slice with what state produced it. But do you know who can label the slices? A hidden Markov model. That is, if we knew the parameters of the hidden Markov model, then we could estimate the likelihood that each slice was produced by a specific state of the HMM. It's kind of a chicken and egg problem. We can label data if we know the model, and we can estimate the model if we know the labels. How do we break this cycle? What if we just made up a model at random? Then we could use that model to label the data, then we could use those labels to learn a model, then we could use that model to label the data. But that couldn't work, could it? I mean, since the initial model is just made up, how could the labels it produces be useful for anything? Remarkably, this pull yourself up by your own bootstraps approach works quite well. The method is called expectation maximization because the labeling step can be seen as computing the expectation, the mathematical average, of the labels. And the model learning step chooses the model that maximizes the likelihood of the assigned labels. Expectation maximization is an unsupervised method. We give it unlabeled data, and it iteratively learns a model that would produce that data. Specifically, it wants to find a model that makes the data as likely as possible. A powerful mathematical fact about expectation maximization is that each iteration produces a model that assigns ever higher probability to the data until it is unable to make any improvements. It's not guaranteed to find the best model, but in practice, it often finds one that is good enough to be useful. In that sense, the expectation maximization algorithm is a lot like the gradient descent procedure that we use to train neural networks. Both start off with a model that is initialized randomly. Both have to discover latent structure that is not provided in the data. Both proceed by iterative improvement. Both have guarantees that these iterations make things better, but neither can guarantee that it will find the global optimum. Finally, both can be applied to many different kinds of problems and produce practical answers to hard problems. Of the two, gradient descent seems to scale better, especially in terms of modern computational devices, and gradient descent seems to be a bit more general. Where expectation maximization requires us to think about a generative model of data, gradient descent can be applied to any setting where we need to search for parameter values that minimize a continuous loss function. Gradient descent can be used whenever expectation maximization is used, but not vice versa. And that takes us to about 2011. By 2011, hidden Markov models have become the dominant approach to speech recognition. These models could be used to produce systems that were free of any two of the three limitations we talked about earlier, but not all three. HMM-based systems could produce recognizers for tens of thousands of words spoken by arbitrary speakers as long as the words were isolated from one another. That is, they were still limited to disconnected speech. Other systems could be used for dictation, transcribing natural speech as long as the system was trained for its particular user. That is, they remained speaker-dependent. A lot of doctors use this technology to record patient notes. Other HMMs were used by banks in interactive systems where arbitrary people could call into a service and make requests by voice. But those systems needed strong top-down priors about what would be said. That is, they still needed a limited vocabulary. Deep learning systems, starting in roughly 2011, made it possible to break free of all three limitations simultaneously. Traditionally, speech recognition systems had been built to turn speech sounds to sentences through a series of intermediate steps. First, low-level speech sounds would be recognized into phonemes. Then these phonemes would be coalesced into individual words. Lastly, the words would be massaged into the most likely sentences. Each layer would send its best guess to the layer above it, but it would also transmit some degree of uncertainty, since language and sound are notoriously ambiguous. Between 2012 and 2015, researchers discovered that they could improve on the state of the art for each of these transformations. The overall progression through the 3 transformations remained the same, but the approach used to solve each of the 3 problem layers became neural networks. For speech sounds to phonemes, convolutional neural networks are remarkably adept at treating a spectrogram as a kind of image and recognizing phoneme patterns in it. For phonemes to words, recurrent neural networks can solve similar problems to those attacked by HMMs and provide latent context for generating the words. For words to sentences, the combination of word embeddings and transformer networks does an astonishingly good job at distinguishing likely and unlikely sentences. Replacing each component of the 3 layers of the system with an appropriate neural network leads to excellent speech recognition performance. The boost in performance surprised Microsoft researchers when their system beat human transcriptionists for the first time in 2016. After working on the problem of speech recognition for decades, they didn't expect improvements to come so quickly. They hailed their accomplishment as a historic achievement. Indeed, the benefits of neural networks for this problem really are remarkable. Because neural networks with the same format and the same training machinery are being used in each component, it's possible to skip over the intermediate representation. For example, phonemes are often viewed as a kind of necessary evil in speech recognition. It's not even clear to the people building the systems that phonemes are quite the right intermediate representation. With the neural network approach, we can train a recognizer to go from speech sounds directly to words. It could potentially create something like phonemes internally, but no person has to tag the speech with these elements. The system could discover its own vocabulary of phonemes, or indeed, not use anything like them. The network can just devise whatever features are most effective in training. Since 2014, there have been attempts to apply end-to-end training, speech sounds all the way to text words, with a single network. End-to-end training is kind of a mantra in the deep learning community. It asserts that we'd be better off not having to pick any internal representations for our networks. As of 2020, such end-to-end systems had been built, but they had not performed as well as the modular approach. But as the research community's understanding of how to design and train neural networks continues to improve, I would not rule out the possibility that new ideas will make end-to-end training for speech recognition viable. Now let's experiment ourselves a bit with a deep learning system for recognizing some simple words. Our system will handle speech that is disconnected and has limited vocabulary, but will make our system speaker independent. Our system could be used for a simple interactive voice response system for a bank, say. The speech commands dataset includes samples of people speaking the words yes, no, left, right, on, off, stop, go, up, down, the digits 0 through 9, wow, happy, Sheila, Marvin, bird, dog, cat, bed, tree, house, and background noise. Let's train a deep network to distinguish yes and no. We'll need to import some standard libraries like matplotlib, pyplot, and numpy, but we'll also need a few specialized libraries for processing sound, specifically librosa and wabfile. Next, we'll get the data file and unpack it into a directory called speech commands. Let's take a look at the raw speech sounds for one of the instances of no. I picked out a file name corresponding to one of the recordings of no. We can load the audio from this file into the vector samples. Librosa.load returns the vector and the sampling rate of this recording. This recording is 16,000 samples per second, which is moderately high quality. For comparison, the standard for CDs, early DVDs, and other related digital media was 44,000 samples per second. If we plot the vector samples for our recording, we can see the speech sounds. No. The library IPython display includes functions for transmitting audio files to your computer's speaker. Calling ipd.audio on the samples we just loaded actually plays the sound. Was my imitation of the sound good?
No.
Ouch. Okay, let's put together a training set. All WAVs and all labs will be our list of instances with their labels. We're going to read in the files for each of the 2 classes of sounds we care about, yes and no. For each label, we assemble a list of all the audio files associated with that label in a list of WAVs. For each file, we run the librosa.load command to pull in the raw speech sounds. To make the training clean and easy, we'll only use clips that are exactly 1 second long. That's 16,000 samples. This operation takes about 5 minutes. We end up with 4,255 instances. We've got our data. Let's organize it into training and testing matrices. We'll import train test split to randomly separate the data into training and testing sets. We'll reshape our audio file into a shape that the network will be able to accept. We'll turn our yes-no labels into 1-0 by testing equivalence to yes. Finally, we can call train test split, where a test size of 0.2 makes an 80-20 split of our data. Let's build a network in Keras for speech recognition. From the Keras library, we'll import the 5 layer types: input, conv1d, and so on. The input layer to our network is the 16,000 samples drawn from the 1 second clips. We'll then instantiate a series of one-dimensional convolutional layers. Convolutional layers detect patterns in local patches of the input in a position-invariant way. Because speech is a one-dimensional sequence, conv1d is a sensible choice. The first convolutional layer will extract 8 features looking at 13 consecutive amplitude samples. These choices are somewhat arbitrary. They're similar to values used in successful vision architectures like VGG16. The second convolutional layer extracts 16 features from 11 consecutive outputs of the first convolutional layer. The third convolutional layer extracts 32 features from 9 consecutive outputs of the previous layer. Doubling the number of features in each convolutional layer is typical for vision networks. The fourth convolutional layer produces 64 features from 7 consecutive outputs of the previous layer. To turn the extracted audio features into a prediction, we flatten the features from the convolutional layer and then put them through 2 dense layers of size 256 and 128. The final dense layer maps the 128 features from the previous layer down to a single output representing the yes-no choice. We set the loss for the network to be mean squared error, then train it for 15 epochs. The trained network has 97% accuracy on new examples. I listened to a few of the clips where the network made a confident but wrong answer. Some had a fairly clear word, but also a burst of noise or very odd background sounds. Some had no word at all, as far as I could hear, and a few others seemed very clear and noise-free. In these cases, the speaking voice was female. It's somewhat common for speech recognition systems to struggle with female and child voices, perhaps because of bias due to too few examples in these classes in the training data, or perhaps because higher pitches might be harder for current algorithms to process consistently. Because networks can end up being less accurate for specific classes of people, it's worth evaluating them carefully before deploying broadly. If the error rates for specific classes are bad enough to constitute a burden on a segment of the population, it might be worth putting the brakes and looking for another solution. Being able to talk to machines and having them understand what we want would make the human-computer interface more natural and fluent. Computer scientists and engineers have been making progress on this challenge for 70 years. Nevertheless, the problem is definitely not solved. Familiar network components like convolutional neural networks, which were pioneered for image processing, were discovered to be exceptionally well suited for speech as well. Moving to neural networks from early methods with human-defined features has led to systems that demonstrate a high degree of accuracy with minimal limitations. But it has meant that the engineers building the systems find it harder to understand what the systems are doing. The frontier of speech recognition has moved away from converting speech signals to text words. The bigger challenge is language understanding. Being able to have a voice-based conversation with the computer involves low-level speech recognition, but it also requires that the machine track the topic of conversation and how the words being said connect to the context of the conversation. This problem is typically addressed in a narrow way by having experts write high-level scripts that keep the conversation moving in a predefined direction. But as we have seen repeatedly through this course, these kinds of hand-designed systems don't scale. Automating the creation of conversation scripts should be a good problem for machine learning. For example, demos of voice-based reservation systems can be impressive in carefully circumscribed settings. Data of people having conversations is gathered. The machines can be trained to process the data. It's not too hard for networks to predict likely directions a conversation might go, but it is much, much harder for machine learners to become effective conversational partners. It seems that learning to have conversations means you need to practice being in conversations, not just witnessing them. Perhaps ideas from reinforcement learning could help. After all, it is an approach focused on doing with feedback, but without needing more explicit oversight from a teacher. The first challenge would be figuring out what rewards the learner should be optimizing in these interactions. The second challenge would be getting patient people for the reinforcement learner to talk to. Figuring out the rewards for interactive dialogue systems is an open problem. But there has been some work on using machine learning tools to discover rewards by watching an expert's decisions. Such an approach can figure out the trade-offs in how a self-driving car decides whether to go fast to arrive quickly or go slow to avoid a bouncy, uncomfortable ride. Next time we'll turn to the subject of how rewards drive reinforcement learners and how we can make machines learn to construct their own rewards. From 1999 to 2006, Sony developed and sold a dog-like robot called Aibo. It came with a set of simple pre-programmed behaviors. But in my lab, we integrated Aibo with machine learning algorithms and used it as an experimental test bed. So it was a sad day for machine learning, or at least for me, when the Aibo was discontinued. But in 2018, Sony began selling a new version of the Aibo robot in some parts of the world, though not the US. Given the advances in machine learning software, it's reasonable to hope that we will see robots for sale that take advantage of machine learning. I worked briefly with the team that became Sony AI. My goal was to get an Aibo to learn tasks from people. Training a robotic dog is just one example of a much broader quest. How do we make our machines understand what we want and then help us do useful things in the world? The answers have implications not only for robo-pets, but also home robots, home automation devices, and even computers in general. At a high level of abstraction, telling a machine what to do goes something like this. A person has an intent or a goal. There's communication of that goal in some form so it can be transferred into a representation the machine can process. The machine then uses this representation as a guide for planning and for controlling behavior in the world. In this lesson, we'll build up to one particular approach to telling machines what to do that uses a form of machine learning called inverse reinforcement learning. But first, it's helpful to start by looking at a more familiar approach. The most direct and traditional way of telling a machine what to do is by writing a program for it in a language like Python. Using programs, people can express literally any computable behavior to the machine. Programming is pretty great, but it's also cognitively demanding. To program, you need to be an expert in what you want to do and in how to express the idea. Programs can be hard to write, hard to debug, and hard to modify. Fortunately for some people, for some applications, we can simplify things in a useful way. I think simplified programming languages provide good gateway exposure to programming, and they might help motivate more people to learn more programming. An analogy I like to use is that everyone should know how to read and write, but not everyone needs to be Shakespeare. So, what's the programming analog of using language to shoot off a quick email? I think the analog of writing someone a note is trigger action programming. It's a highly simplified way to connect real-world activity to programs for controlling that activity. A little trigger action program can turn on the lights when the sun goes down. I use trigger action programs very much like this in my house to control some of the lights and to do other Internet of Things tasks. There are a lot of online services that use this style of programming. The services are designed in a way that makes programs seem simple and friendly, presumably so that almost anyone could write and use them. My collaborators and I decided to put to the test the idea that trigger action programs are easy for people to learn to write. Our results verified the widely held belief that trigger action programs are pretty easy for people. But we also showed that people could handle more complexity than most service providers were willing to allow. The good news, bad news moment came a bit later when researchers at the University of Washington followed up on our work. They found that while indeed people could successfully write complex rules, they didn't know what the rules meant. They couldn't read them. The level of precision required to read, write, and think about complex rules is very challenging for many people, even when the programming language itself makes it very simple to express a rule. To better understand how we might use machine learning to reduce the burden of programming, we can think of different ways of programming machine behavior in a simple two-dimensional space. One dimension is how behavior is specified, direct or indirect. Direct specification means that sensory inputs are mapped directly to behavioral outputs, like in a traditional computer program. An indirect specification uses reward functions to guide machine behavior by assigning scores to different behaviors. The machine's job is to decide what behavior to adopt by interacting with the environment to discover which behaviors maximize those scores. Specifying behavior via reward lets you express the goal that the learner is trying to follow without having to spell out the specifics of how that goal should be achieved. It's analogous to the machine learning idea of using a loss function. Reinforcement learning is the branch of machine learning concerned with learning to maximize rewards. We talked about reinforcement learning in Lesson 13 on games. There, the reward function comes from the rules of the game itself. Typically much easier to express the rules of the game than to express winning behavior in the game. The machine learner is given a reward function, but then generates behavior autonomously. Some of my students built a robotic example of a reinforcement learning problem, a solar panel that learns. The system can take action in the environment by changing the angle the panel is facing. The system was designed to measure energy brought in via the solar panel and subtract the energy needed to orient the solar panel. Then, it was told to maximize total energy brought in. It learned where to point the panel and when. It's an elegant example of using reward to obtain desired behavior without needing to specify the behavior itself, indirect specification. But in more complicated examples, even the reward function can be hard to specify. For example, in 2011, Nest began marketing a learning thermostat that adjusts its behavior via reinforcement learning. A thermostat has competing objectives: maximize user comfort and minimize energy use, making the choice of reward function challenging. Engineers just selected a particular trade-off for the Nest, in effect concluding that most end users would find it too hard to pick a reward function and that the thermostat would be better off just learning from the one chosen by the engineers. A second dimension where machine learning can help with machine behavior are examples and demonstrations. Sometimes it's easier to just show the machine what you want it to do, just demonstrate the behavior, and then let the machine figure out the program. These demonstrations play the same role that training examples play in the machine learning settings we've already seen. A machine learner can learn directly or indirectly from example demonstrations. One direct approach is called learning from demonstration, or LFD, where the machine learner extracts a direct input-output mapping from the examples it sees. It uses supervised learning to learn a rule that generates outputs from inputs that look like the examples it is given. By contrast, inverse reinforcement learning is an indirect approach that observes example behavior and then extracts a reward function that explains the behavior being observed. As of 2020, this promising approach has yet to find its way into deployed applications, but it is possible that the next round of home robots will include this feature. Let's take a look at a reinforcement learning program that makes reward-based decisions from a handwritten reward function. We'll create a little grid world, define tasks in this grid world by defining rewards, and then see what behaviors result when this reward is optimized the way that a reinforcement learner would. Afterwards, we'll use examples from the same domain to experiment with inverse reinforcement learning. We'll imagine the decision maker in this world is a robot in a field. The field is a grid of 50 locations arranged in 5 rows by 10 columns. There are also 5 different categories of locations. You can think of the categories as being types of terrain, say gravel, grass, shallow water, mud, and asphalt. The robot can tell what category each location is. We can allocate different rewards to each category and then see how the robot navigates in response. The variable map is a 5x10 grid with each entry marking the category of the terrain in the corresponding location. Let's have our program display the map. We'll use a library called Seaborn to draw the grid on the screen. We can create a palette of colors for the 5 categories of terrain. Then the Seaborn heat map command plots the map using the colors. Our map has scattered blue terrain, an orange terrain stripe across the middle of the grid, a smaller yellow terrain strip halfway across the grid, and a green patch of terrain in the bottom right corner. The rest of the grid is the white background terrain. We can assign reward values R to the terrain categories. Let's make white a neutral 0, blue and yellow and orange dangerous -1, and green an attractive +10. Next, we need to project these values out into the grid. We define an array matmap, that is rows by columns by categories. Specifically, for each row I, column J, and category K, the entry in the array is 1 if the ij location on the map is category K. Otherwise, the entry is 0. Next, we need to define how navigation in the map works. A robot could discover this information by wandering around in the field and observing how its action choices impact its location. For this demonstration, however, we'll provide the robot with a complete description of how its actions work. We'll make use of a routine called clip that we'll use to keep the robot inside the grid by clipping the coordinate values to within the set of valid grid positions. We define 5 actions, acts, in terms of how each one changes the robot's row and column. The first decreases the row by 1 and leaves the column unchanged. That corresponds to moving up in the grid. The other actions correspond to moving right, down, left, and staying in place. It is common in reinforcement learning to model actions as including stochastic effects. That is, it may be highly probable that the robot's up action will move it up in the grid, but it's also possible the robot might slip to the left or to the right when it tries to move up. However, for simplicity, our example here is deterministic. The array mattrans is the transition matrix. This matrix represents the probability that a given action will cause a one-step transition between any given pair of locations. We fill in this matrix by looping through all the actions. For each one, we enumerate all possible starting locations, row I1, column J1. We define I_next and J_next. They encode the locations that result from adding an action's row and column increments to the current row and column, then clipping the result. Then we loop through all the possible next locations, row I2 and column J2. We fill in the transition matrix with a 1 if the possible next location matches the actual next location, and 0 otherwise. Note that I'm converting the ij locations to a single number, I times the number of columns plus j. That's just to simplify the matrix multiplications we'll use later. Okay, we have the dynamics of the grid world now defined in mattrans, and the mechanism for mapping rewards to states defined in matmap. Now we're ready to compute a way to behave that maximizes rewards. We're going to write our planner using the Keras backend using commands that start k dot. It's a slightly awkward way to program, but writing it this way will tremendously simplify the later step when we'll go from behavior to rewards that explain that behavior. We start off by making a Keras variable rk for the terrain category rewards. Then we take matmap, which is number of rows by number of columns by number of categories, and we compute the dot product of matmap with rk. When we multiply by rk, which has shape categories by 1, we get a new array that is rows by columns. Specifically, it maps each location to its reward value. We use these values as the starting point for our reinforcement learning process, assigning it to v, the robot's estimated best value for being in each location. For the robot's decision making, we need to tell the robot how much to discount future reward compared to current reward. We set this parameter, gamma, to 0.9, meaning a reward retains 90% of its value one time step later. When gamma is close to 1, the robot cares a lot about making choices that will eventually lead to high reward. When gamma is close to 0, the robot only cares about short-term gain, even if that means sacrificing opportunities for additional rewards later. We also define a temperature parameter, beta, that indicates how carefully the robot will choose among closely valued actions. High values of beta cause the robot to reliably choose the highest valued actions. Beta values close to 0 result in the robot being more careless and choosing randomly among the available options. The choice of 10 here results in moderately careful reward maximizing choices. The robot will look 50 steps into the future when it makes decisions. That's a reasonable choice, as the robot can make it across the entire grid world in 13 steps. After each step of looking into the future, the robot considers each of the 5 actions. It computes a value q sub I for each action I. For each example, q0 says, let's multiply the transition matrix for action 0 times the value estimate v. That produces a value for each location that says, how much reward will I get in the future if I take action 0 from this location now? The array q brings all those values together. The array q has one row for each location and one column for each action. The array pi represents the robot's assigned probability to each action in each location. The probability of the robot taking an action in a location is determined by how much reward it predicts it will get, now and into the future, from taking that action in that location. Precisely the contents of the Q array. The higher the predicted reward, the more likely the robot is to take that action. Again, the parameter beta controls how strong the relationship between reward and probability is. The planner has multiplied the action matrix times the values, discounted them by gamma, and then added in the reward for being in the current state. So the planner has completed one iteration of looking ahead. Value v now reflects how good it is to be in each location, looking ahead one additional step. When the loop is completed, v will have factored in 50 steps of look ahead. If this were a chess program, chess grandmasters would weep in envy. But since our little grid only includes 5 times 10 equals 50 states, this navigation problem is a lot simpler than chess. The output of this look-ahead process is an action decision for each possible state. If you're here, go right, but if you're here, go down. In reinforcement learning jargon, it's called the policy, and it is the output of the look-ahead process, planning. The planner also outputs the value function q according to the relationships we previously defined. We can run the planner on the rewards r we defined and observe the result. Here's a path that the resulting policy would follow from the upper left corner. Recall that white locations are neutral, blue, orange, and yellow locations have -1 reward, and green has a positive 10 reward. The robot avoids the terrains associated with the -1 penalties as best it can. It navigates to the location with the positive reward and then stays there. What if we reprogram the reward function so that the green location is only worth 1, while the penalty for the negative colors is much larger, at -10? Well, even though the colors associated with positive and negative rewards are the same, the behavior changes. Now crossing through the orange barrier is too expensive, and the robot remains on the left side of the grid. Let's change which colors are negative. Suppose we associate a reward of -1 with the white locations, +5 for the green location, and 0 for the others. Well then, the robot prefers the colored locations as stepping stones en route to the green location. I think of this environment as the robot trying to stay off of the hot sand. Reinforcement learning is a powerful way of getting agents to follow what we tell them to do. But reinforcement learning requires that we define the reward functions. What about demonstrating desirable behavior rather than writing down the reward function? That would be easier in some cases. Ideally, an algorithm could analyze the behavior and produce a good reward function. How might we demonstrate desirable behavior? If I showed you that an agent selected this behavior, what do you think the agent's rewards look like? This example demonstrates inverse reinforcement learning. Reinforcement learning went from rewards to behavior. Inverse reinforcement learning goes from behavior to rewards. Reinforcement learning is, if you like carrots, go to the carrot. Inverse reinforcement learning is, if you see a horse go to the carrot, it might be because the horse likes carrots. One way to go from behavior to reward is to imagine we select a reward function, then ask a kind of Bayesian question. How likely is the observed behavior given these rewards? That is, we want a reward function that makes the observed behavior as likely as possible. I mean, we could just be looking at random, unmotivated behavior that just happens to take this form, but then this particular path being chosen is pretty low probability. Instead, we can assume that the agent wants to get to green. That helps a lot. The probability of the observed behavior goes way up. Well, what about blue? Well, it might have missed blue by accident, but the likelihood of this particular path increases if we assume that missing blue was intentional. How about yellow? Well, yellow can't be very costly since the robot went right through it even though it didn't have to. But it can't be too cheap, or the robot would have used the yellow locations to avoid the white locations. Orange is harder to say, but it must be no more costly than the value obtained from getting to green, and orange can't be less costly than white because the robot didn't use the orange locations to avoid white. We can formalize and justify this reasoning by taking a Bayesian perspective. We want to know the reward function R that is most likely given the trajectory we observed. We'll use a simplified calculation that's called the maximum likelihood formulation. It says we need to search for a reward function that makes the observed trajectory as probable as possible. To solve the problem of turning a trajectory into rewards, we will need a representational space, a loss function, and an optimizer. The representational space is assigning reward values to the 5 locations of categories: white, blue, yellow, orange, and green. For the optimizer, we will use gradient descent since it's so general purpose. But how about the loss function? The loss function needs to tell us which reward functions fit best with the observed trajectory. So for any reward function, we can derive a policy that assigns probabilities to actions in each location. If you're telling me that in the trajectory the robot chose the down action from location 2,2, that suggests that the robot's rewards caused it to assign a high probability to the action down in location 2,2. In fact, for any reward function, we can look at the probability that the learned policy with that reward function would assign to all of the choices in a given trajectory. That is, we can compute the likelihood of that trajectory given the selected rewards. The more likely the observed trajectory, the better the hypothesized rewards. So let's look for rewards that cause the likelihood of the observed trajectory to be maximized. Equivalently, because logarithms turn products into sums, we want the sum of the logs of the probabilities assigned to the choices in the observed trajectory to be as big as possible. Therefore, the negation of this expression can be our loss function. Let's compute the log-based loss function. The sequence of actions in our trajectory is held in the variable trajacts: right, right, down, 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 etc. Once the robot arrives at the green square, it executes the stay action a few times before we cut it off. We need to convert this sequence of actions into a sequence of locations. You could write out the sequence of locations explicitly, or you could sum things up in a simple loop. Or, as I decided here, you could use a little fancy Python programming and apply a Python command called reduce to run through the sequences of actions from left to right and return the sequence of locations starting from 0, 0. The important result is that we now have a sequence of actions in trajacts and a sequence of locations in trajcoords. To compute the loss, we run through this sequence of actions and look at the computed policy pi. We ask pi what probability it assigns to the ith action in the sequence at the ith location in the sequence. We take the negative log of that value and add it to the loss. Now we have a way to connect the rewards to the loss in a single function. We can use gradient descent to search for a reward function that produces low loss. We pick a learning rate and an initial random value for the rewards R. Keras can compute the gradient of the loss with respect to the rewards. We'll call that value grads. Next, we can create a Keras function that takes the rewards as input and produces the loss and the gradient as output. We'll call the combined loss gradient function iterate, since we'll be evaluating it at each iteration of gradient descent. We'll run for 5,000 iterations, taking the rewards R and producing the current loss and gradient via the iterate function. We'll then move the rewards R a small step in the direction that decreases the loss. Every 100 steps, we'll output the current loss so we can measure the progress. Here's what we get. The loss decreases very quickly at first, from around negative 12.3 to around negative 10.8, then flattens out. The reward function reached at the end assigns a very small negative value to white and yellow locations, a slightly larger negative value to orange, and a much more negative value to blue, and a much larger positive value for ending up at green. The algorithm successfully inferred an approximation of the robot's preferences from this single example. The algorithm I just described takes in demonstration trajectories to estimate rewards. So now let's talk about where the demonstration trajectories come from. My colleagues and I have found that people demonstrating desired behavior distinguish between whether they are just doing an example of the behavior or whether they are showing someone else how to do the behavior. Consider the case we get if we tell someone three things. Orange tiles have a penalty, the goal is to get to yellow, and the safe colors are white, blue, and purple. The path on the left is a reasonable example to satisfy the goal under these constraints. The path on the right is equally good as an example of doing, but the path on the right is a more complete and informative way of showing someone all the tile colors that are safe and which have a penalty. We recruited people online and asked them to either do, solve the problem, or show, demonstrate a solution to someone else so they could do it. Here are paths taken by 60 participants. A few were confused, but the majority of the people in the show condition do some extra traveling to highlight where the safe cells are. They wiggle back and forth across safe boundaries, like between white and blue and purple. The kind of behavior you'd expect if the demonstrators are reasoning about the mental state of the observer. They're being better teachers. Indeed, our inverse reinforcement learning algorithm makes better use of these more instructive demonstrations in learning. When we train an inverse reinforcement learning agent to extract the rewards from do demonstrations created by people, the learners are about 65% confident in the result. But if we use show demonstrations created by people, the learner's confidence rises to 92%. My team and I even went one step further. We created a new inverse reinforcement learning algorithm that specifically reasons about why the teacher chose the particular demonstrations that were chosen. Basically, the new algorithm asked itself, what reward function would I demonstrate if I were trying to teach someone the rewards? This kind of recursive reasoning takes place all the time when we humans are communicating with each other. It's hard, in general, to reason across many levels of communication at once. But this grid problem was small enough that we could write a simple recursive reasoning program to solve it. The learner using the show demonstration and this recursive reasoning is 98% confident in the correct task. Using inverse reinforcement learning to create trainable learning systems will provide us with better ways of delegating to our machines tasks that we want done. That will empower more of us, providing ways for people with good ideas to put those ideas out into the world to benefit others. Some researchers, such as Stuart Russell at Berkeley, think that these intent-conveying ideas, like inverse reinforcement learning, are even more significant to the future of our society. The thinking is that these ideas may be a way, perhaps the best way, to address concerns about malfunctions in hypothetical future computer systems that are super intelligent. A typical doomsday scenario begins when we ask the machines to do something relatively innocuous, like improving the speed with which they can look up data in a big database. Being dutiful optimizers and powerful problem solvers, they conclude that they will produce better solutions to their given problem if they seek to improve their own capabilities, assure their own survival, and take control over more and more resources, like energy and raw materials. Steadfastly pursuing these intermediate goals would put the machines in conflict with what people want. People also need resources, and people are apt to turn off a machine that is competing for the same resources. So stopping people from stopping the machine would become a natural goal for the superintelligent machine to take. In fact, the fewer pesky humans there are around the world, the less likely the machine's goals will be thwarted. At the root of this robot apocalypse scenario is an idea that a reinforcement learner can overfit to the reward function it is given. The presumption is that the machine learner will devise a policy that maximizes the specifics of the reward function it was given without being able to generalize to a broader set of circumstances. One solution to this problem is to make sure that machines realize that there is uncertainty in the goal they are given. The goal they have might be missing key elements like improved database access time, using only existing capabilities and resources, and without killing any humans. Learning tasks from people using some version of inverse reinforcement learning might be the key to keeping powerful machines, and even adorable IBOs, working in the service of humanity.